Hello and welcome back to my video on writing ionic formulas, and this time it's going to be part 2, and we're going to be looking at how to write polyatomic ions, which can be actually a really scary subject for a lot of introductory students. So we're going to be following the same steps as last time with the first video. So we're still going to be writing our predictable charges, we're going to be writing the symbols side by side, and we're still going to be using our swap drop method. So I saw the periodic table here, so in case we need it, we have it available. But what polyatomic ions are, so it's a very set chart of of ions that are all bound together. So we have all these individual elements that are, most of them are bound to oxygens. So what these are referred to in this case is called oxyanions. So with oxyanions, we're always going to have some sort of nonmetal that I'm just going to label X for now, such as maybe like carbon, sulfur, nitrogen, that are bound to a set of oxygens. Now, this number of oxygens, or N here, always has a set charge for that polyatomic. So for example, one could be where I have like CO3 2 minus. So with this one, we have a carbon bound to 3 oxygens, and it's always going to have a 2 minus charge to it. So in this case, this one is known as, this one's carbon, right? And the ending for this in terms of naming is 8. So we'll have carbonate would be the ending. So like another type of polyatomic is this, typically it's editing the number of oxygens in the charge. So, or sorry, in the actual element. So if I kind of go one less and I say, all right, the charge is going to stay the same and we have CO2, 2 minus, then in this case it would be carbonite in this situation, right? So carbonate, carbonite, just showing that oxygen subtraction. So there is a table that I put together for this. So for polyatomic ions, the big thing about it is it's all about how we go through naming them and trying to understand them. But with this, we're just going to focus on balancing and writing chemical formulas more than anything else. So with this individual chart, we're going to be mainly focusing on more like carbonates, like things like the eights and ite endings, and then a little bit of the different polyatomics here as well. So we're going to focus on balancing. There'll be another video in the future on naming, but we're going to focus on formulas for this video. So let's get to it. So some different things. So with these, we follow the same rules. We're going to write our metal first. So let's say if I have two different species, we'll have sodium, and then we'll have chlorate as our two species. So how do we go about trying to show how these things are going to be bonding together? So first thing is sodium. What is the predictable charge? We'll go to our periodic table. So with this, we can see, all right, sodium is right in that first column here. So that's going to be a +1 charge. Now for chlorate, we have to go to our polyatomic sheet. And what we can see is all right, well, chlorate is right around here that I'm highlighting in a light purple. We'll circle that as well. So we see it's ClO3 minus 1. So let's write those down. So we have Na plus and ClO3 minus. So how does this work in terms of balancing charges and swap drop? Well, the way that we have to imagine it is that the entire polyatomic is one single unit. So it's one unit for the polyatomic, okay? So meaning that it's almost as if this entire thing is in parentheses and the whole molecule has a -1 charge as a result. So when we swap drop this, what we're doing is the +1, where the 1 in this case, it's going to go outside the parentheses, and the -1 is going to go still in the same spot as normal. So when we write this, how is that going to be? Well, being that they're both 1, that charge is going to get dropped. So it's going to just be same as always. The sodium chlorate would be the name for this molecule. Okay, so sodium chlorate. And like I said, we'll go over naming in the future, but we're just dropping those charges. Let's do one where the charges are not quite so equal though. So let's say if I have the following where I have a cobalt 3 plus, and we'll also bound that with, we'll do bisulfite. So with this one, when we have bisulfite, that's HSO3 with a -1 charge. So how does that work entirely when it comes to the different prefixes? Let's talk about it for a second. So sulfite is a 2 minus charge. So we can see that right here, right? We have sulfite S3 2 minus. So whenever there's a hydrogen in front of it, or it might have the prefix bi in front of it, it edits the charge by 1. So you can see that the charge is only -1, and there's a little hydrogen that is sitting in front of that when it gets altered. So every time we add a hydrogen, you can see that the charges go from 2 minus to 1 minus by adding a hydrogen. So let's go back. So we have that HSO3 minus. Now, how are we going to swap the charges? Well, like I mentioned last time, this is one entire unit. So when we drop that, the 3 plus, or that 3 is going to, the numerical value 3 is going to come outside of the parentheses. And then the 1 from the minus is going to go to the cobalt. So when we write that, cobalt will be cobalt 1. We'll have our parentheses, which is just HSO3. And being that cobalt had a 3 in front of it, we're going to put that next to outside of those parentheses. So it's going to be cobalt 1 HSO3 3, essentially. So when we name that, this would be cobalt 3 bisulfite. Now, what does that look like on an elemental picture? Well, it's kind of the same thing. So being that we have one cobalt, it's as if we draw just one CO3 plus, and let's just put that in its a little atom, and then we have around it a bunch of HSO3 molecules all bound around it. So we have these little polyatomic ions all bound around, and being that there's 3 of them, we're going to be drawing 3 individual polyatomics on each side. So that's what it looks like on the molecular atomic picture right here. So this is our molecular picture where we have those individual polyatomics, and that's what those parentheses are representing when you put that 3 outside of it. So let's try a different one. So if we do, let's say we'll pick calcium and phosphate. So we'll have phosphate, which is PO4, and we can try to find that on our sheet here. So it's PO4 3 minus, so that would be the charge for that one. So we'll go back and we'll write that charge down. So let's swap drop it. So we're going to bring both those numbers down. We're going to write our parentheses around PO4. The number is going to come down. We'll swap drop it. So what is that going to make? Well, the calcium had the 3 value come towards it. And now the phosphate will have 2 come next to it. So we'll write that as our 2. So what does that picture kind of look like? Well, it's almost like we have 3 calciums bound together. So if we kind of try drawing that, let's just put like alternating. We'll have calciums here and here, sort of like this. We'll draw them in their little elemental orbs. And then being that we have, for every 3 calciums, we have 2 phosphates. So we'll put like maybe in the middle here, like 1 phosphate. Excuse my handwriting there. I'm drawing it sideways, and then we'll have another phosphate like maybe over here, like just showing that it's that 3-to-2 ratio is really the important part here. So that's a little bit of the basics of it. So let's try like a different one here. Maybe one from like a famous painting or something like that, just to kind of make it fun. So if we do, let's say, if you ever looked at the painting, so a lot of polyatomics exist in a lot of um, different foods that we eat. Maybe a lot of the medical industry uses them a lot. So like foods, you see them in like chips, for example. Like sodium acetate is a common preservative slash like flavoring agent that you'll see in chips. Or maybe for casts in the medical industry, polyatomics are really common in those. So this one, I have the picture for Starry Night from Vincent van Gogh. And it's one of the most beautiful paintings made. And this one actually has a polyatomic in it. So this has iron 3 cyanide in it. So what is that exact structure? So if we kind of look at this, well, that 3 for iron tells you that, all right, well, we have iron 3 plus. Now, what is cyanide though? So why don't we go to our chart? And what we're going to see is that if we look at our miscellaneous ones here, that cyanide is Cn minus. So we're going to use that one and go through this particular example. So we'll have iron and Cn minus. So when this is going through this, we're going to do our swap drop. We're going to put parentheses around Cn. The number is going to come next to it. So if we rewrite that, that's going to be Cn in parentheses with a 3. And then the 1 from cyanide will come over to iron and it'll be FeCN3. So, and this is the color for Prussian blue. So this is one of the, what really gives it that blue color that we see here in the Starry Night painting. So I hope this video helped a little bit in how to use polyatomics and how to make sure you are balancing them correctly when you're writing your ionic formulas. I hope you have a wonderful day and come back next time for future videos. Thank you so much.